First, electricity. The section on electricity is divided into energy transfer in circuits, mains electricity, and electric charge. First, energy transfer in circuits. Here's a quick reminder of what circuit diagrams and their component parts look like. To start with, these are some of the standard symbols used in the electrical circuits you might see in your exam. You'll also need to use them yourself if you're asked to draw a circuit diagram. They are a single cell battery, a switch, two symbols for a lamp, a fixed resistor and a variable resistor, and an ammeter and voltmeter. Here's a simple circuit with a battery, a switch and a lamp connected in series. When the switch is closed, a current begins to flow, pushed around the circuit by the battery. The current leaving the battery is the same as the current returning to the battery. Because all the components in the circuit are connected one after the other, in series, the current is the same everywhere in the circuit. In this case, 0.2 amps. Current is measured in amps, with an ammeter, which can be connected in series with each component to measure the current flowing at that point. This is a parallel circuit, where the current can split up and go around different branches of the circuit. The current flowing in different branches can be different depending on how easy it is for the current to flow that way. Ammeters connected in different branches of the circuit will show different measurements. One thing we do know is that the total current flowing into any point in a parallel circuit is the same as the total current flowing out of it. For example, at the junction where the wires join, there's 0.6 amps flowing into that point and 0.2 amps flowing out down one branch and 0.4 amps flowing out down the other. That's 0.6 amps altogether flowing out from that point. Next, we'll look at ways of changing the current in a circuit. The current in a circuit can be changed either by changing the voltage or by changing the resistance in the circuit. First, changing the voltage. We're most familiar with the voltage in the case of a battery, where the voltage is the difference in energy between its two terminals. In fact, voltage is the difference in the energy between any 2 points in a circuit. Voltage is measured in volts with a voltmeter. To measure the voltage, you connect the voltmeter in parallel with the component. In this case, the voltage across the battery is 6 volts, while the voltage across each lamp is 3 volts. More battery cells in the same circuit mean a higher voltage and a bigger current. In this circuit, if the battery produces 3 volts, the current is 0.1 amps. If it's 6 volts, it's 0.2 amps. And if it's 9 volts, it's 0.3 amps. The other way of changing the current in a circuit is to change the resistance. One way to do this is to change the number of components, such as bulbs, in the circuit. Bulbs are designed to offer resistance to the flow of electricity. That's why they glow. More bulbs in the circuit means a greater resistance and smaller current. Adding different resistors in the circuit can also change the resistance in the circuit. The greater the resistance, the smaller the current. Resistance is measured in ohms, written using the Greek letter omega. An easier way to change the resistance is to use a variable resistor that can change its value. Again, the greater the resistance, the smaller the current. The smaller the resistance, the greater the current. Resistors are specially designed to offer resistance to the flow of current. They're used in electric and electronic circuits to control the flow of electricity through the different components. In a circuit, energy is spent overcoming resistance. This energy is given off as light or heat, which is made use of in light bulb filaments and in the heating elements of kettles, hairdryers and other heaters. As well as the components, like bulbs and resistors, the connecting wires themselves have some resistance. Thin wires offer more resistance to current than thick wires because they have less space for the current to flow. Long wires have more resistance than short wires, the same thickness. So, to summarise energy transfer in circuits. Current is measured in amps, and it's not used up as it passes through components. The current in a series circuit is the same everywhere. The current in a parallel circuit splits up to take different routes. More current takes the easier route, that offers less resistance. In parallel circuits, the total current into any junction equals the total current out of the same junction. More cells in a circuit mean a higher voltage and so a larger current. More components in the circuit mean a greater resistance and so a smaller current. Short wires have less resistance and carry more current than long wires. Thick wires have less resistance and carry more current than thin wires. There's a special relationship between the voltage, current and resistance in a circuit called Ohm's law. Ohm's law says that anywhere in a circuit, V equals I times R, where V is the voltage across a component in volts, I is the current going through the component in amps, and R is the resistance of the component in ohms. If you know any two of these values, you can work out the other one. A good way to remember Ohm's law is to put the values in a triangle like this, with V at the top in the vertex and R on the right. So V equals I times R. I equals V divided by R, and R equals V divided by I. Another way of stating Ohm's law is to say that the voltage is proportional to the current, as long as the resistance and the temperature stay the same. If we plot a graph of current against voltage for a normal resistor, it's a straight line. As you increase the voltage, so the current increases in proportion. Double the voltage and it doubles the current. A bigger resistance needs a bigger voltage to push the same current through it. The graph will still be a straight line, but with a flatter gradient. You might have spotted that the straight line graph continues into the negative quadrant. What do you think that means? When the straight line graph is in the negative quadrant, the voltage across the resistor is negative, which means it's been connected the other way round. The graph also shows that the flow of current is negative as well, which means that when the resistor is connected the other way round, the current just flows the opposite way through it. There's more about Ohm's law in the physics part of the higher tier science programme. That's the end of energy transfer in circuits. This section is about mains electricity. The important thing to know about mains electricity is that it's different from battery electricity. Battery electricity is direct current, DC, while mains electricity is alternating current, AC. A battery supplies a steady voltage, so the trace on the screen of a cathode ray oscilloscope is a straight line. The voltage of an alternating current supply is changing all the time. The main supply in the UK changes 50 times a second. But why is alternating current used for our main supply?
There's a fundamental difficulty with transmitting direct current, and that is that over long lines, the electricity is slowly lost.
The first user has plenty of energy, but as you move further down the line, less and less energy is available to the user.
Where has this electricity gone? It has gone in the form of heat, heating the electrical lines themselves. Therefore, the electricity is not available to the end user on a long line.
So the problem with DC supply is that it loses power over long distances. AC does not, because it can be transformed up to higher voltages or down to lower voltages for different stages of its journey. AC electricity is also easier to generate. From the power station, the grid uses high voltages of up to 400 kilovolts to send electricity over great distances along thick cables that don't introduce much loss of energy. The supply can then be reduced to a safer 240 volts for use in the home. That's still a dangerous amount of energy, and precautions are needed to ensure safety. The 240 volt electricity supply comes into the home through the meter and the fuse box. A fuse box has fuses or circuit breakers to protect each circuit in the house, such as the downstairs lighting, a cooker, or a ring circuit of wall sockets. Each ring circuit has several sockets wired in parallel across the live and neutral wires, so each has the full 240 volt supply. Mains electricity arrives at the plug through the live wire, passes through the appliance and returns through the neutral wire. Look carefully at how a 3-pin plug is wired up and which wire goes where. The earth wire doesn't carry a current unless something goes wrong. All the wires are insulated to stop any current passing between the wires, and there's another fuse in the plug. Wall sockets are also earthed. If there's a fault in an appliance and the metal body touches a live wire somewhere inside, a person touching it could be killed. The earth wire allows electricity to flow to earth through the earth wire, blowing the fuse and not going through the person.
A fuse is designed to allow several amps to flow before it melts. Its purpose is to prevent fires. It won't prevent electrocution. What does protect you is a residual current device, or RCD. Receiving an electric shock will still hurt, but the risk of electrocution is much less. All circuits have 2 connecting wires. The current flowing in each wire should always be the same. If you accidentally touch a bare wire, the leakage is immediately detected by the RCD, causing a switch to trip.
Describe 4 safety features that can be used in domestic mains electricity supplies. The safety features you should have noted are fuses, which are thin wires that get hot, melt and break the circuit if too much electricity flows through them. Earth wires that conduct electricity straight to earth if there's a fault in the appliance. Insulation around the wires and plastic casing around appliances. And RCD circuit breakers, which are more sensitive than fuses and can react immediately to tiny electrical leaks and shut off the supply. There's more about electrical power supply in the physics section of the higher tier science programme.